Okay, so the three integrals that we computed before will be called orthogonality relations because secretly what we're doing is we are computing inner product on a vector space. So, and this is a very big topic. Yeah, but let me just explain. Even if you don't fully understand, try to understand as much as you can. Okay? So first of all, there's something called an L2 space over an interval a to b. And these are functions. These are collection of all these functions. It's a set of functions where if you take the absolute value of x, the absolute value of the function, you square it, and you integrate from a to b dx, this value has to be finite. Now, any continuous function will be a finite thing, right? But for example, if you have a function that's like 1 over x, right? You may have to define at 0, let's say it's 0, okay? Yeah. Then what's the integral of this thing squared? It's like, let's say the a to b is 0 to 1, okay? So 0 to 1, and you square this, it's 1 over x squared dx. And that integral is negative 1 over x, and you plug in 1 and 0, and then of course when you plug in 0, this is not a finite thing, right? It becomes infinity. This is minus 1 over 0 plus. It's an improper integral, so you really have to replace 0 by 0 plus, and if you do that, then you end up with positive infinity. And you can see it by drawing the graph. The graph is like that, so if you integrate from 0 to 1, goes to infinity, and this area underneath is infinity. However, there are functions that go to infinity and still manage to be in L2. So what I just, this calculation immediately shows that 1 over x does not fit in the L2 space from 0 to 1. On the other hand, let's say you have like x to the quarter power. This still will somewhat look like this one, right? But if you integrate this squared from 0 to 1, it's going to give you. Oh, by the way, don't write notes on this one. It's like not so important. It's just to help you with the concepts. It's never going to be asked in an exam or anything. It's just, if you understand, it's good. If you didn't, it's not a big deal. So if you square this, it's like 1 over square root of x, right? Because this is a fourth root. So if you integrate this, that's what? 2 radical x, 1, 0. So it gives you 2. So it's a finite value, right? So this calculation shows that 1 over x to the quarter power does belong to L2 of 0. Okay. So it's, in general, it's very tricky to know which one fits in there or not. But you can think of such a set, right? Now, there's some hard inequalities like the Cauchy-Schwarz and some other ones, which shows that if you take any two functions from here and you add them together, it will again belong to this set. Okay? And that's what you learn in mathematical analysis if you ever took that course. Did anyone take that course? Mathematical analysis? All right, no. All right. So if two functions, you add them, it's still in there. And also, if you take any function and multiply by a real number, of course, it will still belong in here because it's a constant multiple, you can put it outside, right? So you can multiply anything by a number and it will still be in here. What does that mean? It means that L2 is, the L2 space is a, huh?
Linear?
It's a linear space. More technically, it's a vector space. For it to be a vector space, you have to check a little bit more, which is that 0 belongs in here. Okay? And if fx belongs here, negative of fx should still belong here. And they both check out. Okay? So you can see that this is actually a vector space. Okay? So if you took the abstract linear algebra course, things that you learned there applies fully in this space. It's an infinite dimensional. It's a very, very big space, so dimensionally it's infinite dimensional. But it still satisfies all the axioms of a vector space. Not only that, there's a well-defined inner product in this space, which is if you take any two elements in here, fx and gx, and then if you integrate from a to b, then this thing we denote it as fx gx, the usual way you write inner products. This will satisfy all the axioms of an inner product on the real space. If you could also let these functions to be complex valued, in that case you have to put this bar in there, then this right side will be something called a Hermitian inner product. Now, none of what I said would make sense if you haven't taken abstract linear algebra. So that's that, okay? But you did learn something similar. Everyone here took multivariable calculus, or else you can't be here. And in multivariable calculus, if you have two vectors, what can you do with it? You can add them. You can do a scalar multiplication. That's what I just said. Adding two vectors belongs to, again, it produces a vector. You can take any scalar multiplication. It's, again, a vector, right? But can you multiply two vectors? There is no multiplication of two vectors that gives you a vector. Only in dimension 3, there's something called the cross product, right? Yeah. But there's another one where you take two vectors and it gives you a number. What's that? That's called a dot product. Yes, yes. So I said in technical terms that this is an inner product, but inner product is just a generalization of a dot product. So this thing is like a dot product, and if you think about it, that it's exactly what it is. Like you have two, so fx is like a function, but see from a to b you have a function, right? Then its coordinates are like values at each of these x's, right? And then you evaluate these coordinates and you multiply coordinate-wise, right? That's what you do. For dot product, you multiply coordinate-wise and you add them up, right? And adding, because you have infinitely many ones and it's not even countable, it's like, so you can't add them by just doing sigmas. You have to do the integration. Now if you do the integral with these, then it's like a dot product. Okay, so what we're doing here is a dot product of two functions. Okay, and if two vectors have a dot product of 0, what does that mean?
Orthogonal.
Orthogonal. That's why it's called orthogonal linear relations. These three are called orthogonal linear relations because what we're doing is we're doing the dot product and 0, dot product is 0, dot product is 0. Of course, if you do a vector, so here's another thing. If you have a vector dot product with itself, this is always equal to norm squared. There's a norm of a vector, right? It's norm squared. So when m and n are the same, you're essentially taking the vector multiplied with itself. You're doing the dot product of the vector by itself, right? And of course, it's not going to be 0 because the only vector with 0 magnitude is the 0 element, right? But these are not zeros, okay? So that's why you get a non-zero value, and that happens to be pi. And this one. Okay. So in the grand scheme of things, what's happening here is that there is some gigantic vector space, which is really hard to imagine, but you can talk about basis of a vector space. Let me see, how many of you know what a basis of a vector space is? Yeah, what's the basis?
It was a set of, it was a linear combination. You can get any vector in the vector space by using linear combination of bases.
That's correct. Okay, so with just one more condition. So, a basis of a vector space is when you have a set of vectors from that vector space, where any element in here can be represented as a linear combination of those things in the set. However, there's one more condition. It has to.
They're orthogonal.
No, that would be orthogonal basis. Bases don't have to be orthogonal. It happens to be orthogonal. The one that I'm about to introduce, it happens to be orthogonal. Okay. The condition is that it has to be a minimal such set. So if you take any element out of it, then there will be vectors that you cannot represent with the smaller set. Okay. So it's like any set which is minimal in the sense that taking any one of them out fails to represent every vector, but if you have them, then any vector can be represented here. Okay. So I wrote here Fourier series, and usually because people don't expect everyone to have seen linear algebra and mathematical analysis, they don't talk about this in the textbook, but if you actually talk in these more technical terms, then what's happening is a lot clearer. What's really happening is this. Fourier claims, here's the Fourier's claim that one, you have to have one. Okay? One sine nx with actually we need 1 over square root of 2 pi, square root of pi, and then cosine of nx over square root of pi. And that, you know how to normalize a vector, right? If you take any vector, then the normalization of a vector is the vector divided by its size, right? So, because v dot v is v squared, the norm of this function is square root of pi. So you're just dividing by its size. Okay? So these are unit vectors in this space, okay? Not only that, if you do dot product among themselves, and in any combination, with n equals to 1, 2, 3, so on and so on, then this set, with n being 1, 2, 3, and so on, forms an orthonormal basis of L2. That's what Fourier is saying. Fourier's contribution is that any vector or any function which is square integrable can be represented as the linear combination of these things. And initially this doesn't make any sense at all because see, these are very nice functions. Those are continuous functions, right? But as I said in the examples I showed you, you could have like all these pathological functions that could have like discontinuity. It could be even going to infinity, still be in L2. And this claim is very bold. It's saying that whatever that function is, you can take this as the basis and then just represent it. And when you represent it, it means that it's equal. And it's very weird because it's saying that you're adding up all these continuous functions and you still manage to produce these infinite like functions or functions with discontinuities. So when Fourier first, he needed this to solve the heat equation. When he first said this as a way to solve a heat equation with any initial condition, people didn't believe it. There's no way adding these continuous functions will give you a discontinuous function. So that's the idea.